Okay, thank you. Gee, I mean, I understand this is not your regular jug night, so I'm really surprised to see so many people here, but it's really cool. I have this talk here. We call it Performance Tuning with Cheap Drink and Poor Tools. The tools actually won't be that poor because we'll actually be using Visual VM. Has anyone used Visual VM here? 1, 2, you should put your hand up. Now, Roman should put his hand up. I think, yeah, exactly. 3, 4. So there's a few people that have used the tool, and it's really a nice tool being delivered by Sun now. And I think since I had the opportunity to talk to the NetBeans profiling team just prior to coming here, I have some ideas that it's going to be even nicer in the very near future. Okay. So, anyways, So really what I want to do here is do mostly demo, because I find that with performance tuning, it's nice to listen to someone, but it's much better if we can actually do it. And so that's what I hope to do with you tonight. Right, so little slide about myself. So I think the slides will probably be made available so you can take a look if you need to. Mostly I just do performance tuning engagements, and I also teach a performance tuning course, and so the next offering is here on those dates. So if you're thinking of trying to avoid winter for just a little bit longer and you want to learn something about performance tuning, then I can say this is a great place to learn. Right. So I want to start my talk by saying, reading you this statement. Okay, the resemblance of any opinions, recommendations, or comments made during this presentation to performance tuning advice is merely coincidental. Okay, so we got that right. So what am I saying here? I'm saying that performance tuning is an activity where you're going to look at the environment you're in, and you're going to try to make your application or make your system run better within that environment. In other words, it's a very highly localized activity. And things that work here might not work over there because you're just not in the same locale. So you always have to take the performance tuning advice, tips, recommendations, whatever you want to call them, and basically evaluate them in your own environment to see, are these things going to work? Now, in this particular presentation, what I hope to give you is maybe one tool to help you evaluate performance and to make a sound judgment as to whether this is actually going to work or not. So, you know, what are we here for? We're here to answer this particular question. You know, why is my application running so slowly? Well, generally our applications are running slow because, well, we're dealing with a computer system, and a computer system is a bunch of all of these non-shareable bits that are thrown into a box, and then we try to launch a whole pile of processes on this machine, and we're trying to share all these things. And you know, if you can't get to that thing, then you're waiting for it, right? We're waiting to get to that non-shareable bit. And generally what we're, you know, with performance tuning, we're trying to figure out, okay, where are we waiting? What are we waiting on? And how can we not wait on that thing? How can we get this thing to work, to cooperate with the other things that are happening in the system so that we get an application that runs according to our performance requirements. So, you know, I'm going to introduce this little model that I use. I think some people are probably familiar with it here already, but generally what people try to tune is they try to tune the application. This is traditionally where we're all educated. How many people here are developers developing applications? 1, 2, 3, 4, 5. How many people's arms are still functioning after a long day of work? Can we see arms? Can we have arms up? Okay, great. Okay, so you know, university, we're in one, right? Actually, there's an interesting story about this university. This is Charles University, right? So just as a slight aside, before we get into this box, you know, my fun story is much more fun than this one. So I worked for a company out of Portland in 1998, and this university published a benchmark. They compared my company's products with a bunch of other companies' products, and our company's products did not fare well in the benchmark. Now, I hope I can say this and still get out of here alive. The university, or the people at the university, didn't happen to do a good job at the benchmark. And I'm saying that not just because they trashed the product that I was working with at the time. You know, we just looked at it and said, okay, there's a lot of things they missed. But the fun part about the whole thing was that we had American lawyers contacting the university, trying to have them withdraw the paper that they had published, because you know, they had violated the license agreement according to U.S. law. And you know, my comment on the whole thing was like, you know, what the hell do a couple of academics in Prague care about U.S. law or U.S. licensing agreements? So it was, you know, it wasn't looked on favorably, my comment anyways, but you know, it's quite true. I mean, who here cares about U.S. law? No one's willing to admit that they're not, right? They don't care. This is being recorded, so don't worry. It won't be released on the internet. Okay, anyways, back to application. Right, so we're in a university, and this university, I guess, does maybe not so good a job at benchmarking, but I'm sure they do a really good job of teaching you how to deal with that, with the stuff that's in that box, right? And you know, there's a lot of other educational institutions on the planet that are also exceptionally good at teaching you how to deal with stuff in that box. That's where you're trained to work. That's where you work. If you've got a problem, where are you going to turn to? Right there, right? That's what's causing the performance problem. So that's where we're going to look for the problem. And unfortunately, you've all been trained incorrectly. That's not the place to find a problem, right? There you're tuning an application. We don't tune applications, we tune systems. And systems are more than just the application, right? There's a whole bunch of other stuff that goes in there, right? So we have all of these bits. We have a Java virtual machine, we have an operating system, and we have hardware. Okay? So all of these things have to be taken into account when we're performance tuning. When we lay out a description of our system, okay, we're going to say, okay, what type of CPU do we have? What's its speed? What's memory capacity do we have? How fast can we write to it? Disk I/O, same thing, right? Network. What's our effective capacity, throughputs on these things? So we want to understand how much hardware we have. What's the capacities of the hardware? What's the rates? This is the currency of our system. Okay? We have another layer in here. We have the operating system. This is the thing that's going to, shall we say, it's going to allow access to the hardware. It's going to provision our scarce resources. Our scarce resources are our hardware. We have a Java virtual machine. The primary activity of the Java virtual machine, as you know, from a performance perspective, is memory management. So it's provisioning memory to our Java application. Our OS might be provisioning memory to our JVM, okay, but internally we're going to do more fine-grained provisioning at the JVM level. And on top of this is sitting our application, and really all our application is doing is just basically providing some means for users. Yeah, okay, we're the users. The users are also part of our system, right? You know, what goes here? Well, something is missing. We need some dynamics in their system. This is a very static thing. This is the thing we're going to use to drive the load on the system. Those are our actors. So what are our actors? They're, well, our end users, batch processes, other machines that might make use of our system. Maybe they make calls to web services or something. Maybe you have some RESTful services. You know, whatever the technology is that they have to interface with you, they're going to use that, and that in turn is going to drive load on the system, and how they drive load on the system is going to determine how your hardware is being spent. That's, like I said, the currency of your system. Okay? But that's not the only determining factor. It's like, how did you code your application in accordance to the work that you need to have done? How does the JVM manage memory under these situations? How does the operating system interact with all these things, right? So inside this box, we want to look at, okay, not only utilizations at each layer, but we want to look at interactions between the layers. So what the box is suggesting is that, okay, we not only want to look inside each of these boxes, so we need tooling to do that, but we also need tooling to look at the interactions between the layers, okay? So when do we need to do that? Well, we need to do that when we're not meeting our performance requirements. In other words, we have a performance bug. That's when we're going to start the tooling. And the first thing we're going to do is we're going to start looking at the hardware. We're going to see how is the hardware being consumed, and we're going to use that information to try to help us determine what type of tooling is going to best expose the problem that we're looking for. You know, so what do we need? We need monitoring tools, things that are going to tell us what's going on. We need the application that's going to act as our benchmark, our thing to benchmark, right? Of course, we need hardware. Hardware, you know, basically, if you look at this, if you write a description out of what's all in that complete stack there, including how the actors behave, what we're doing is we're describing one system. If we change one component or one piece of that description, we're creating an entirely new system. And if we have an entirely new system, we potentially have a completely different performance problem. And I'll give you an example, right? How many people here have had a performance problem in production? They tried to reproduce it in their test environment, and they can't reproduce it. Yeah, just about everybody, right? So, you know, why? Well, because you were tuning a different system, completely different system. Unless your production system is identical in every way, in every aspect, in each four of these layers to your production environment, you're tuning a different system. Right, which means that, you know, we need this other thing called a load test harness. What's the load test harness going to do? Well, it's basically going to simulate the actor layer, the layer on top. What else is included in the harness? Well, everything that's needed to support the test. In other words, data is also part of our test harness. Right? It's not just an application driving load. It's also the things underneath that are supporting how that load is being received and being processed. Okay? So we run into a performance anti-pattern quite often called data light. And what data light says is that we do not have production volumes of load in our system, and because we don't have these production volumes of load in our system is simply going to cache everything. And caching is a very effective technology. It works very well. It prevents you from making calls to slower underlying technologies. You know, we don't make that trip to the disk drive. We don't make that trip across the network. Yeah. Oh, that's better. Nice hissing noise gone. Okay. And because we don't make those trips, you know, if we don't make those trips artificially, in other words, we're data light, that means we're not going to be able to reproduce the performance problems that we have in our production environments. If we go back to actor layer, right? It's very important to try to get this layer to be representative of what's going on in your real application, because if you don't have a representative set of usage patterns, or you know how load is being driven down on the system, as that doesn't represent what's going on, then you're basically going to stress different parts of the system. And when you start looking for a problem, you're generally always going to find one, and you're going to fix one. The question is will it be the right one, the one that matters, right? This is a place where teams tend to spend a lot of energy and a lot of time fixing the wrong problems and redeploying only to discover they haven't fixed the correct problem, and then they have to go through cycle after cycle after cycle, sometimes lasting 1, 2, 3, 4, 6 months, a year. Some problems are never solved. Okay, so example, typically an easy one to solve, memory leaks. Who here has experienced memory leaks in their application? Right, how long does it take you to find them? Any answers? No, that's a serious question.
Like a day.
A day? That's pretty quick. Anybody else?
Like a year.
Like a year? Okay. I've heard that answer also. Like never? Some answers. Anybody else? Anybody else going to say, how about it never? No? 1 month? Yeah, 1 month? Yeah, well, that's the other issue too, right? How do you discover these things? 2 months? Anybody for 3 months? Well, I mean, what I found is that, you know, an average memory leak costs a company about 50,000 euros to fix, on average. Right? So when you say a day, like you're in the 99th percentile, right? For doing it, so that's pretty good. Now, if you can get that down to half an hour, then you're probably about as efficient as you're going to get. Because that's about how long it should take you to find a memory leak. But that's just one example of problems that, you know, and that one's easy to reproduce because it's not so sensitive. I mean, that's really an application bug, and it's not so sensitive to its environment. However, it is very sensitive to the actor layer. If you're not exercising the right usage pattern, you're not going to find it. Okay, so here's a process we're going to follow in the demo. So let me read it out here. We're going to take our application, we're going to baseline it. So we're going to find out our initial response times for our important usage pattern. We're going to also ask the users, okay, what would they like as a response time? We're going to do a comparison. And we're going to say, okay, does the performance meet the requirements? If so, we're done. If not, we have to go in through a performance tuning loop, right? So user's not happy, make sure the user has money, got to pay the bill, right? We're going to use some key performance indicators to sort out what type of information we need to get from the application. And we're going to use that information, you know, we're going to use now the appropriate tool in order to get that information out of the environment. So we're going to profile to some level. Generally, we use monitoring for key performance indicators. That'll tell us which profiler we need to use, and then we're going to profile. From the profiling, we should fix, QA, and then rebaseline. Did our fix work or not? Did we meet our performance requirements, or do we have to go for another iteration, right? So the key performance indicators we want to look at are CPU breakdown. We want to look at user time versus system time. And we want to look at how memory management is working. Okay? And we're going to use that to engage in this activity that I call identifying the dominating consumer. Now, the dominating consumer is that activity or that thing that's happening in our system that's controlling how the CPU is being utilized. In other words, there's a lot of things that we do that will prevent the CPU from being fully utilized, and we need to identify those, and we need to find the nature of them, because that's going to help us identify the underlying fundamental problem in our application. Right. So it turns out we have three candidates for dominating consumer. We have operating system, we have the Java virtual machine, and we have the application. There's also another possibility that nothing is dominating. Okay? So we have no dominating consumer. And in those cases, we want to try to figure out why. So one nice example is the Scala compiler. Sorry, Bill, I have to mention this. So I was working with Bill Venners, and he said, "Why is my Scala compiler taking so long?" So I dropped it on here and ran it, and I said, Bill, there's no dominating consumer here. And the CPU utilization is such that leads me to believe that the Scala compiler is single-threaded, right? Which is a bit ironic. I thought it was kind of funny because Scala is supposed to be good for multi-threaded concurrency stuff, and well, I guess I found it ironic. Nobody else does, but it's okay. Right. So in this situation, there was no good reason why we shouldn't get good CPU saturation, except for this whole thing was only single-threaded, right? And sometimes, other examples of that, thread pool sizing in application servers, connection pool sizing. Sometimes they're just too small, right? And we'll get into a situation where there's no good reason or no apparent reason why we shouldn't get good CPU saturation. In that case, we'll say, okay, nothing is dominating. So it gets into a couple of these questions. If my application is slow and the CPU is at 100%, we're going to ask, what task is consuming the CPU? Is it the JVM or is it the application? And in order to sort that out, I'm going to use garbage collection logs. So I'm going to do an analysis on the garbage collection logs. It's going to tell me, is garbage collection running efficiently? Java memory management running efficiently? If so, then it's my application that's at fault, and I'm going to do execution profiling. If not, it's my JVM that is causing the grief, and I'm going to do object creation profiling or some other type of profiling that's going to indicate how my application is using memory. If my application is slow and CPU is not 100% used, the question is, what is keeping my task out of the CPU? Now, it could be that we have no dominating consumer. It could be that we have a very bad application operating system interaction. In the case where we have a very bad application operating system interaction, we want to find out what the offending problem is. And generally, that involves only a small number of things. And we can probably list them. It's nothing new. Everyone's heard of these things. Disk, network, locks, right? Lots of context switching in our application. So, really, there's nothing surprising in the list, right? And we just get the appropriate profiler and we can find them. Right. So with that short introduction, I'm just going to say, we have a reasonable idea of how to tune a system. So why don't we just go and tune one? So we'll go to demo. I'll take any questions anytime. Feel free to interrupt. It's okay. So probably what I should do is to make this easier, go to turn on mirroring. Okay, my screen's ugly, but that's okay. So we have a smallish application here that I'm going to run. And before I run it, let's see if anyone picked up any tips from the whole thing. Anything we should do, or anything you would like to know or see before we actually start performance tuning this application? Let's see how well you were listening.
Is it a standalone one or is it running on application server?
I'm sorry? It's a standalone application, yeah. There's no application server involved. I thought of giving the application server one, but that takes much longer to tune.
What's your hardware configuration?
What's my hardware configuration? Mac i7, 8 gigs of RAM, 512 gig SSD.
And the number of cores?
2 hyper-threaded.
Is something already using
Good question. Let's monitor what's going on. So we do want to bench on a quiet system, which is why we're not screencasting, because that was taking up just too much CPU. Okay. It's not 100% quiet, but the things that are running, I'm not going to shut them down for the purpose of the demonstration. So get over it. Next.
What do you expect from the application?
Good question. Fantastic. He's been awake. I would expect that this application should run in less than 1 second when we're finished. Anything else? Okay. So our first activity is to identify the dominating consumer of the CPU. What type of information do we need to get that done? As you can see, you guys are actually going to tune this. I'm just going to stand here and prod you. Garbage collection logs. Excellent. Okay, let's see if we got some of those. Yeah, garbage collection logs are a must. Should always turn them on all the time. Is that big enough to see? Tell me when it's big enough, because I got a real close-up view. Got them turned on. Let's turn on something else here while we're at it. Okay, compile it. Okay, anything else we want to look at? No, just our little monitoring tool that we have running up there, right? That's all we really need. Okay, so between garbage collection logs and monitoring tool, let's baseline. Okay, a little pause in there. We're going to run it up and processing. 1, 2, 3. I think we're past a second. 4. If we weren't, it would be a really boring presentation. Well, more. Okay, what do we got here? Processing. Okay, we're past a second, so because we're past a second, we should be trying to identify the dominating consumer of the CPU. For 5 points, who is the dominating consumer of the CPU? You think it's what? Mac OS, the operating system. Why would you say that? It's a good guess. Okay, I need a reason, or you don't get your 5 points. No one can identify the dominating consumer. Probably because I didn't give many good rules for it, okay? Dominating consumer Java application, CPU utilization by the system is greater than 10% or equal to the amount of user time. Approximately equal time. Now, I/O isn't a choice. Operating system, JVM application, those are our choices. It could be what? Either the JVM or the operating system? So I say application. Okay, let's put the choices on the board here. I see I got chalk. This is really quaint. I'm used to whiteboards. Is it okay if I mess up the boards here? I'm going to do it anyways. App. JVM. Ooh, lovely. OS brings back fond memories. Okay, how many vote application? Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You know, you put your hand down. Do I need to run it again for? Because no. What do the colors mean? What do you mean? What do the colors mean? Red is for operating system. Green is for user space. Good question. We'll just run it again. So we'll get another blurb out here. JVM. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, or 20. I'll say about 20. It's a rough guess. Operating system. That's the rest of you. So I guess. Operating system, who's voting? 1, 2, 3. Don't know? 4. Don't know? 1, 4. That's amazing. Okay, let me explain this to you again. The operating system is the dominating consumer of the CPU when it exceeds 10% of total CPU utilization or is equal or approximately equal to the amount of CPU consumed by the user. Generally also supported by an inability of the application to consume 100% of the CPUs that are available. Who's the dominating consumer? Should we revote? The operating system. Yeah, I mean, that's clearly, the red is clearly more than, unless you can't see red up there. I can't see from here. Maybe I'll go back over here. Okay? Clearly, I can see red. That the operating system is well over 10%, and it's certainly equal to user time, or approximately equal to user time. So I'm going to declare the operating system, well, I'm going to declare myself to be ineffective at lecturing to start with. Okay, so the operating system is the dominating consumer here, because it is, okay, it's meeting that criteria. So the real question is, what does that mean? Sorry? Improper use of operating system calls. Well, there is certainly some bad application operating system interaction. As I like to say, the application is treating the operating system like a rented mule. Right. Right. Okay, so how are we going to find it? Anybody have any ideas? Dtrace. Yeah, I could possibly use dtrace. So I could pull up instruments on the Mac and use dtrace. That would probably work. That would work in Solaris. What happens if we're in Linux? Yeah, I could use vmstat too and just look at like what the threads are doing. Well, okay, so it's a standalone application, so there's obviously no socket activity, right? Well, I mean, what are the operating system interactions, right? Disk. It's not writing to disk. I don't have a disk. Okay, but it's not doing disk-like I/O. Network, not doing that. So that pretty much leaves locks. So if we play this game of elimination based on looking at these different measurements, we'll quickly find that pretty much locks is the only thing that's left behind. So let's bring up another one of these. So JVisualVM is a tool that's distributed with the JDK. If you download it from the web, it's VisualVM. If you get it for the JD bundle with the JDK, it's called JVisualVM. And we can use this. It's got all kinds of nice little tools in it. Let's start up our application again. Oops, we don't need to compile. We just need to run. Okay. So what it's using is it's using the attach on demand feature that's available in the JDK 1.6, right? So what we're saying is that the JVM is pre-configured to accept connections from different sets of tools. And in this case, what we're going to do is we're just going to do thread monitoring to try to understand what threads are doing. So we'll use attach on demand to attach to an already running process. That's why I put the pause in there, so I give myself time to attach VisualVM to this process. Now, after the attach, it's going to instrument classes. And you notice I turned sharing off. Well, that's another feature that's available in the JDK 6, is that we have class sharing, which means that my VM is going to load the classes, and after it loads the classes, it's going to do all of the verification, validation, manipulation, and then it's going to take those and store them off in a file in the JDK directory. and the next JVM to start can just load those classes directly without having to do all this validation. Now, I don't want to instrument shared classes. Visual VM doesn't like it. It tends to crash, and other bad things happen, so we want to turn that off. Okay, so as you can see, Visual VM has discovered that I've started up this process here, and now I can just double-click on it and open it up. And now that we have it opened up, I got a whole bunch of different panes here, so let me get rid of this so it's not bugging us. I don't know how big this is, how visible it is. Oops, what's going on here? Hello? Do I see lockup or what? Okay. Okay, it's sensible from where it's draggable. Okay, so we can see all this stuff here I got? I don't know how visible it is from the back. So from left to right, I have an overview of what's happening in the JVM, so I can take a look at JVM arguments, system properties. You know, I can get a really nice breakdown of what's going on. Here I can monitor what's happening in terms of CPU, GC activity, threads, how many threads are running, how many threads are live. I'll go back to this one later. Here we have a profiler that we can do CPU profiling, or we can do memory profiling. Lots of features in here we'll probably look at later. We have management beans. These are things that are written into the JVM that allow us to monitor what's going on inside the JVM or interact with things in the JVM. So for instance, with the logging, there's the possibility that I can come in here. If I'm using JDK logging, I can come in here and I can set the log level to debug directly, or I can set it back, up to some other level directly. Let's get log level, logger level. So the logger level is null in this case because I'm not using JDK logging. And if I have JDK console plugin installed, which I don't yet, that means there's another tool called JConsole that's distributed with the JDK that gives you access to a bunch of this information. I can actually install things that were intended for JConsole. So these tools are all, well, this tool is written on the NetBeans platform, and it's very extensible. So you can write your own plugins fairly easily for it to do different things. In the next version, it appears like we're going to have a probe interface, and with the probe interface, we're going to be able to extend this in some very meaningful ways. Right, okay. Let's go to our thread monitoring. Yeah, looks good. So green is good, that means go. Red is bad, that means we're waiting on a monitor. The yellow is just in a wait state, and blue is sleeping. So basically all the threads we're looking at now are just JVM threads. They're just regular threads. There's no application threads running here. So let's go and take a look. Profiling, monitoring, processing. Okay, so here's all our threads. Anything we can notice about what's going on and any action you'd like to take? What do you think? Sorry? Too many threads? A lot of thread locking going on here. Okay? Tons of thread locking. Okay. So unfortunately, we missed our window of opportunity to take some more action, but that's okay. We can fix that. What would you like to do in this case? What's the simplest thing we could do? Thread dump. Okay, take a thread dump. Excellent. So let's turn that off. Let's restart our application. Now, the one thing we want to do when we're profiling is we want to make sure that, oops, yeah, I might have just blown it. Let's see. Threads, here we are. Okay, our profile's developed. Let's take our thread dump. Okay. So you can see conveniently placed on the thread monitoring panel was a little button that said take a thread dump, and then I get something that looks like this. Now, who wants to analyze this? Okay, did I hear a lot of not me's? Excellent. So let's use this tool instead. This is called Thread Dump Analyzer. Okay, so this is a Visual VM plugin. So you go to the Thread Dump and the TDA website, java.net, and you can download it and install it as a plugin. So what is it telling us? Well, it's reading the thread dump, and it's basically organizing the thread dump into meaningful categories. So we have 33 threads running, threads waiting for a monitor. That's the one we're interested in because of all that red. Threads sleeping on monitors, and threads locking on monitors. So there's a lot of information here. And you can get a monitor view of what's going on. So there's 10 monitors in the application. So let's take a look at this one. So you can see, what a surprise. All of my worker threads have shown up here. Yeah? And they're all waiting for monitor entry. So let's pick one. I don't know if you can read that. I'm sorry, it's like kind of like small. Can anyone read that? It's big enough. I'm half blind and I can read that. So, okay. So what is this thing saying? We have a diagnostic yet? Sorry? Yeah, so it's waiting this thing on this monitor in line 24, right, of the find person by name. Okay, what about this one? Looks like the same. Looks like the same. Looks like the same. So I think there's a pattern here that's emerging very slowly. Okay, now what would you like to do? IDE. Look at the code. Okay. This is exactly what we want from a profiler. We want a direct vector into the code. You notice we've not said what this application is doing. We've not described it at all to you. We don't know what the components are in it. Actually, we know nothing about this application, right? But we've identified that it had a problem with synchronization, and now we have a direct vector into the code. So by completely ignoring the application code, we've actually managed to very quickly find a problem together. And this is exactly what we want to get from profiling tools. Right, okay, so let's go over here and go, you want to go into the code? That's right, so let's see. What class do you think you want to go into? Person storage? Was that the one? .java? Okay. Line 24. Let's make this bigger so it's less ugly. Okay. So this is a bit of an abstraction of a problem that we actually see in a lot of systems. We call it like over-synchronization. Let's see the issue. Okay. How do we want to fix this? What's that? Sorry? Remove synchronized? Okay. We can do this safely because we're using the synchronized map. Okay. Now, who here believes that this is going to be the end all, this is actually going to cure this problem? Nobody? Does anybody believe it? Yeah, okay. Well, we'll allow for a little bit of dirty reads on the other end. I'm sorry. Can you shout?
We should
Allow for a concurrent read from the map. How would you propose to do that?
Oh, actually, no, I take it back. There are two different maps.
Okay. Somebody wants to use a concurrent hash map. Okay. So if we're going to change the threading model in this class, like let's go whole hog, right? Let's just do a good job on it. I mean, there's two trains of thought here, right? We've made a change to the code, and at this point we should test it to see if that solved the issue. But let's just do that, because that's only going to take a second. Okay, let's go back over to here, right? So who's the dominating consumer of the CPU? It's still the operating system, right? Okay. And at 19 seconds, we really haven't done much to help with performance. So again, we should run it again. Whoops. Stop that. Let's get an attachment here. Close off that. Cancel. Start it up. Threads are running. Wait. Thread dump. TDA over here, and not really a surprise. We're looking at, oh, is that different? So we've moved the bottleneck along, but it's effectively in the same place. So let's just go and fix that. Oops. Everybody happy with that? Okay, let's compile it. Hopefully it compiles. I didn't miss anything, did I? Compiled. Okay. Let's run it. So rebaseline. What do we need for rebaselining? Okay, so, oops. Press enter, off we go. Warm-up time 2. Processing, 1001, 1002. Well, okay, that's a lot better. But it's still not under a second, is it? So we got another problem. First thing we want to do is identify who's the dominating consumer of the CPU. Well, we only have a little bit of data to choose that from, but take a look. Who's dominating consumer? So we have a lot of people saying application. How many say application? 1, 2, 3, 4. How many people say JVM? Quite a few more. How many people say operating system? Nobody. Excellent. Okay. Fantastic. How many people say we don't have enough information right yet to know? That's the correct answer. Thank you. We don't have enough information. Why? The JVM and our application are running in user space. So they're running in the same process space. So we need a differentiator at this point in time. We need something to say it's the JVM or the application. So that's garbage collection logs. So in that case, I'm going to use this tool, HPJmeter, free download from HP. Okay, and let's do an analysis on the garbage collection logs here. Okay. Now, what do we got? Besides a tool that has fonts that are too small to read. Well, from the top, we have, basically we have a bunch of information that says NA. So if we're running an HP JVM, then this works very nicely. If we're running a Sun JVM, then it works, but not quite as nicely. So what we want to look at is the GC activity summary, last occurrence, the count. So we have 662 collections occurring, 2 full GCs. And then we can look at the average GC rate. So we're like at 65 gigabytes per second. That's pretty cool. So that's looking kind of hot. We're looking at overall GC efficiency. What's that, 2.606%? For this type of application running under these conditions, we definitely want it to be under 10%, but surely under 5%. Okay? On a regular application, we probably want it to be closer to 1%. You have to sort of, this is one of those fuzzy numbers that you have to look at the situation and weight the value here. But what that's saying is that the garbage collector is running 2.606% of the time, which is a pretty healthy figure, I think, for this type of application. If you have periods of inactivity in your application, of course, then you want to have a lower tolerance in terms of how much garbage collection activity you want. Now, there's another problem here. There's a GC to full GC ratio, which is the magenta color on top of the purple. It's a nice color combination. And, it was guys from the San Francisco area that wrote this. So anyways, that looks really high. I want full GCs to be, actually I don't want any, but I really recognize I'm going to have to tolerate some occasionally. I certainly want that magenta sliver to be as thin as you possibly can get it. And it does seem kind of thick. So let's go here and take a look at this. It's like, oh, okay. Well, these 2 GCs I can explain. Those at our application startup or JVM startup, you're going to get 2 technical GCs being called. So system.gc being called from inside the JVM for no good reason, no good apparent reason. I mean, there's technical reasons to do it, but not because heap is full and we need to collect it. And then, my gosh, this is heap utilization after garbage collection, and it's like this. That could be a memory leak, except for one important thing. There's no full GC. Without a full GC, we can't do a memory leak diagnostic. Okay? Because this could be just like objects are leaking into tenured space, and they won't be cleaned out until we do a full GC. But upward sloping heap utilization, it's like frightening to look at. But I think this one is okay. Duration. Well, these garbage collections are happening really, really quickly. So I don't think there's any deal with pause time at this point here. I'm going to go over to this one here, and I'm going to look at another view at that. I'm going to say percentage time in GC. I'm going to see that when I weight time in GC over percentage time in GC, that, it's running 5. There's 2 bands, one at about 5%, one at about 7%. And that's, I'm pretty happy with that. If that's garbage collection took only that amount of time, I think there would be nobody complaining about garbage collection. However, when I look at this number, I'm going to see this huge band running at about just a little bit above 4 gigabytes per second. That's how much memory is being allocated, or that I'm churning through. Now, this number is a little hard to evaluate. You actually have to go back to your OEM and figure out how fast your bus is, how fast your memory chips are. But from that, you can actually figure out what your effective throughput or your memory bandwidth is. Okay? And in this case, on this particular piece of hardware, I believe I'm pounding the crap out of my memory bandwidth. So my object creation rates are just way too high. Now, garbage collection is working very efficiently, but that's because I'm letting the objects die young. And the cost of collecting an object in young generational space is almost zero. So even though I have an object creation problem, I don't have a garbage collection problem. I'm going to declare the JVM to be the dominating consumer based on this analysis, which means we need to go into memory profiling. More specifically, we're going to look at allocation stack traces. Okay? Should we go ahead? Everyone get that? Questions? Dissenting opinions? Wonderful. Can't believe there's no dissenting opinions. Okay, so let's go here. Blah. Let's run it. Let's go back to Visual VM. We don't need that anymore. We go over here. We double click on that. We go over to our profiler, hit settings. You following all this? Memory? Okay. So quickly what I did was I just basically connected back up to the running JVM, and I got over to set myself up to do memory profiling. So I don't need this information, so I'm going to back it off so I have lower overhead. And what I want to do is I want to record stack trace allocations, but I don't need it for every object. So let's just back off the overhead of profiling by saying, let's just collect the stack trace for every 500th object that's being allocated. Okay? Actually, you know, let's be daring. Let's say for every thousandth. Yeah. 1 in 1,000. That's all we need to collect. Right? Okay. In that case, memory, profiling, wait for the instrumentation to attach. Bingo. There we are. How's that look? And let's run our application. And let's take an snapshot and get allocation stack traces. I don't know how long that's going to run. It's still running. Okay, I could have done it again. No, it doesn't matter. Okay, so we have an idea what's going on here. So what we're looking for is elephants. Big red things in this case, right? So okay, so why did I pick on car? Well, obviously I picked on car because it was the number one thing. By far, far and away was the number one thing. Looks like it's still running. Let's just use it. Let's go for another one here. I'll use a snapshot. Yeah, okay, see if there's anything else. With these things, what we want to do is we want to let the profile develop. We want to get past the startup anomaly. If the startup anomaly dominates the profiling, then you're going to be tuning the wrong thing. So make sure you're in a nice steady state before you capture a snapshot to do the analysis. Now, I mean, this one is going to show the same thing, but there's a whole bunch of other things that are showing up also. Okay, so we're interested in these big red lines. Voila, voila. Okay. We see anything there? Or is that too small to read? So this is the causal execution path for all those cars being created. What's really nice about this technique is that what we find in most applications is that there's about 10 or so causal execution paths responsible for about 40 to 60% of all the objects being created in your system. That means you have a small number of reasons why your system is creating objects. And you can usually tackle them one at a time very quickly. Okay, anybody see any problems here? Okay, remember, we're looking for a vector into the code. Where's our vector into the code? Right there. Okay. That looks like a hit. Let's try this one down here, the second one. We have a couple paths here. Whoops, that looks like class loader issue. Okay, what do we see here? That's the bottom again. Where's our vector into the code? Find person by name. Okay, so a pattern is starting to emerge. And we really want to keep at this till we're absolutely sure of what we're looking at. Anything else here? Nothing different, right? Okay, what do we want to do now? Check the code. Yes, exactly. We have a direct vector into the code, so let's just follow it. Let's see where it takes us. Okay, I got to do some technical disconnect here. Done. So it's pointing to that. This is an abstraction of another problem we run into in code quite often. Use what?
Buffer.
Use a string buffer? String builder. Use a string builder. Well, if I go back to the profile, okay, so how many people like that suggestion? Use a string builder instead of a plus. 1. 2. Sorry? Oh, we don't have to think. We can see it right here. What's that line say? That says that the compiler is already changing the plus to be an abstract string builder, right? So it's already using a string builder under the covers for us. That's okay. But I like that you made that suggestion. He's my straight man. I'm sorry?
There was an expand.
Because of low capacity.
So can you carry the string builder and set the capacity because
Okay, you want to do that? Like that? Like that? Where's the typo? Oh, LENGT8. There's your, okay, thanks. Okay, then what do we want to do? Like that? Like that. Import what?
could be just a different for the back.
1001, 1002, 1003. Oh, we have another suggestion. Oh, and we blew it, right? Where's our monitoring at? Oh, there it is up there. Dominating consumer. We don't know. It's not the operating system. Let's go to HP JMeter. Let's run it in the background this time. Ah, look at that. Wow. More stuff happening here. Wow. Heap utilization is nice and flat. Durations are still okay. Creation rates have come down quite a bit, but I'm still thinking that Yeah, it's improved the situation, but it actually still looks like we have an object creation problem. Should we, yeah?
How does it classify? Yeah, and what should we use, like, if we calculate the key for the mass different values, like that we don't have to concatenate, the string, but we can calculate the key, for example,
Okay.
like different values without creating new.
So you want to move that variable up to be a non-local variable then, yeah? Right. I'm not sure I understood what you're saying. Maybe because I'm not hearing so well.
What about making patterns by hash maps or
Hash maps of hash maps. Right. So I've actually had the privilege of, or the honor of making 3 contributions to 97 things every programmer should know. And the one contribution that I made that didn't make it was collection of collections is a code smell. I don't like stinky code. So let's go back to your suggestion. We'll get back to you though. Don't worry.
I would use just like integer, lookup by integer, when I will use like combine hash code of the first name and surname.
Yeah.
And use it as a key for the lookup.
Oh, okay. So instead of actually, okay, use. Okay, gotcha. Now I understand what he's saying. That's an interesting one. I never thought of that one. Did everyone get what he said? Okay, so in this case, what we want to do is we want to, what do we want to do? Oh, yes. Okay. Sorry. If I had used an ID, I would have caught that mistake readily, right? Okay. You like that? Collide. Yeah, we have that problem with it already. Yeah, I think, but yeah, but that is that's a problem.
So how about creating an express class like domain, implementing a hash code, and using an instance of this class as a key?
Oh, okay. Well, that's another interesting idea. Oh, sorry. What did you?
Yeah, on the ground place. I don't see that the problem is here with 5 bytes. So we should look much higher than here.
No, it's actually there. The profiling directed us right here. That was our vector into the code.
But let's have a look to the caller of this class.
Why? Give me a motivation reason why I want to look at the caller of this class. Do I have a vector into the code? I mean, this is one of the things where we actually have to fight our training. Our training is we're trained to look at code. And it's really difficult to go into a problem that's rooted in code and stay away from the code. But that's how you be effective when you're performance tuning. So my typical engagement is 1 week long. I don't have time to read code. I certainly don't know anything about an application when I walk in on site. okay? So the only way to be effective, get the job done within the week, is stay away from the code. You want to use the tooling to tell you exactly where to go. So in this case, the profiler gave us a direct vector into the code. We know that we have a string concatenation issue. So he's, you know, the solution being proposed now is basically saying, okay, if collection of collections was a code smell, then, you know, why is it a code smell? The code smell is because it's, you know, the collection of collections is ambiguously describing a relationship between the data in one collection and the data in the other collection. And instead of ambiguously describing it, maybe we should explicitly describe it in the form of a domain class. In this case, we're using two fields to do a lookup in a hash map. If we were doing using two fields to do a lookup in a database, what would we call that? Sorry? Composite key. Exactly. So let's do the same thing. Okay? Are we happy with that? Okay, have our monitoring in play here. Bingo. Okay. So by introducing this missing abstraction, we actually eliminated the need to do the string concatenation altogether. So it's not free. We do have a little bit of extra object creation going on, but the extra object creation is much less than the object creation that was going on with the string concatenation, which is why this works. And we find that if you have missing abstractions in applications, that tends to lead to performance issues, because you're doing things to work around not having that abstraction to make things, you know, to glue things together. You know, to your point of looking above, sometimes you do need to look above, but you need to have a good reason to look above. In this case, there was every indication that the problem was not above, but actually below, and that's the profiling was telling you. But sometimes you do need to go above. Yeah. But you want to resist trolling around in code aimlessly. Otherwise, you're just going to get lost, and that's very ineffective in this situation. So if you have a good reason to go trolling, you know, you want to do it with an execution profiler, something that's going to follow a code path, that's going to take you through your vector into the code. Okay? Questions?
The implementation of that composite key.
Oh, yeah, yeah. Yeah, sure, sure. So it's just a dumb data holder. Okay? Any other questions then? So as you can see, you know, the process was very rigorous and very methodical. We start off by baselining, identifying the dominating consumer, using that to understand what the underlying problem was, and then applying the appropriate profiler based on that information. And we did that very iteratively until we met our performance requirements. Yes?
I have a question. In allocation, does it depend on how large chunks I need? Because
Yes.
yeah.
Yeah. Allocation depends on a lot of different factors.
If I need 2 bytes or 10 bytes, it's actually a chunk. I can find it.
Well, because we're allocating in young generational space, we're on like a fast path allocation. Fast path allocation is effectively a pointer bump. So it doesn't matter if you go after 2 or 100 at that point in time. But there's different optimizations that could be applied to smaller allocations, right? You know, you're not going to allocate a megabyte array on stack, for instance, or in register. That's going to have to be allocated directly out in memory, which has implications where if you have a small object, it's possible that you could allocate it in registers only, which means it never touches heap. I've heard one statistic saying that 50% of all objects are dead by the time they leave the register. So 50% of the write bandwidth in most applications, well, is used for writing dead objects to memory. That's how quickly they die. Any other questions? Fantastic. Yes?
Could we optimize it even more?
Yeah, if we actually create the composite key on a thread local, we can turn the garbage collector rate off. You probably only gain about 100 milliseconds, right? So you'll save a bit of object creation time and the collector will be completely turned off. But I'm sure it's not worth the effort in this case. It might be. Any other questions? Fantastic. So I guess you can go and solve all your performance tuning problems now. Yeah? Great. I think we're pretty much done, yeah. I think we're at about an hour and a half. Thank you very much for coming to listen, especially on such short notice, and I appreciate you hosting me here.
Thank you very much.
Yeah, okay.